thank you very much for the invitation today. NSF doesn't often get called by the Electrochemical Society to speak at one of your meetings, and I am absolutely delighted to have the opportunity to address this crowd. We are excited to be new partners, and we'll look forward to working on a more continuous basis with the ECS. So, let's see. So for those of you who are not very familiar with the National Science Foundation, we were chartered in 1950, so we're a relatively new agency. And our mission is to promote the progress of science, to advance the national health, prosperity, and welfare, and to secure the national defense. In other words, health, wealth, and stealth. So that is us. The NSF budget is about $8.1 billion this year. It's the highest that it's ever been. And along with the science in all areas of STEM, we are really strongly engaged in preparing a workforce for the future. So this is the general map of the organization of NSF. Our director is Dr. Franz Cordova. I actually work in the math. I don't know if this will work. This works. This way? No? Okay, I'll just point. I work in the Mathematical and Physical Sciences division, so that's chemistry, the division of materials research, physics, astronomy, the division of mathematical sciences, so that's the 5 of us. We are the largest directorate in NSF. Other directorates include biological sciences, computer information science and engineering, education and human resources, engineering, geosciences, and the social, behavioral, and economic sciences. So those are our companions. I will speak in this audience just to chemistry, but if you have questions about, thank you very much, the Division of Materials Research, or our partners who are very interested in the Electrochemical Society and very much seeking a partnership as well, that's the chemical, biochemical, engineering, and transport systems, so in engineering. So for the 3 of us, we're all very interested in working with you going forward. I'll make sure I do this correctly. Okay. Sorry. So for chemistry, as I said, the chemistry budget's about $250 million a year, and most of our funding goes into the individual investigator awards. So we call them the IIAs. That includes single investigators from faculty members from universities, colleges, etc., and small teams, 2, 3, maybe 4 or 5 people. Our basic disciplinary research programs are listed here. We receive about 2,000 proposals each year, and so we're very much in the business of, accepting proposals, reviewing proposals. You probably have all, gotten requests from us at some point. And our fund rate is about 25% for most of it. That's much higher than engineering, which funds in the single digits. So we feel that's a fairly healthy success rate. The average award size for chemistry is about $450K over 3 years. Our career awards that go to young faculties are about a bit bigger and a bit longer. They last for 5 years and are approaching about $650 right now. We have, in this past year, limited submissions to 1 submission per PI per year. And that is a strategy mostly because we want people to participate in the big ideas and other activities which add to our budget. I'll be very, very frank. All of these other activities can add to the chemistry budget, so kind of one bite of the apple for the core, and then we hope you, keep submitting, proposing into the big ideas and the other activities. So chemical catalysis and chemical synthesis are very much interested in receiving proposals from this community, especially for electrosynthesis, electrocatalysis, big areas of research right now. We're super excited to have that. The Chemical Measurements and Imaging program looks for sensors and other aspects like that. Environmental science, also looking at sensors. The chemical structure, dynamics, and mechanisms A and B programs look at thermodynamics and kinetics. So if you're interested in those topics, propose to them. And the macromolecular, supramolecular nanochemistry, MSN, and that's what I'll call them from now on, is all about nanoscience and things like that. So if you're interested in any of these, we have 2 submission windows, September and October. This is a couple of the highlights I kind of threw in here as kind of commercial breaks. I'm not going to tell you about other people's work, although we do often really appreciate hearing about the results from people's research. This one is to remind me to talk to you about sustainability, which is a key area of interest for the chemistry division. We're interested in sustainability in all respects, so use of non-petroleum feedstocks, doing things with base metal catalysis. Electrochemistry may fall in there. CO2 reduction, nitrogen activation, all kinds of topics we're very, very interested in. And clean energy, another highlight. This is from the CSDMB program. We're looking at flow batteries, any kind of technology that resemble solar research, water splitting, all kinds of topics like that we're very keenly interested in. Clean energy looks to be a topic that will be very hot in the next year, so you can look forward to us kind of looking for proposals, especially on those topics, sustainability, clean energy. So what I'd like to do with you today is kind of go through some of our programs, giving you an idea of where the sweet spots might be for if you're submitting proposals, where we would like to fund more. Not all of these programs will be for everybody, and I'm happy to kind of slow down and define the acronyms, because NSF can get really quickly, deeply into the acronyms. So if I go too fast, just give me a heads up and I'll slow down. So the first one is the Research Experiences for Undergraduates program. We host REU sites. The REU program has a budget of about $4 million per year, which doesn't sound like very much, but we fund about 50 sites. This is for undergraduates to dip their toe into the research experience. And the deadline for that is coming up in August. So I definitely want to encourage people, if you're willing to host a cadre of 6 to 10 undergraduates and get them interested in research, we'd definitely like to have your proposal, and soon. The GRFP program, Graduate Research Fellowship Program, supports master's or PhD level students with a $34,000 stipend to them, $12,000 educational allowance, and it's pretty much a very nice honor for graduate students to get this. It's money that they have, so they get the money, and then they can go shop around to whatever research group they would like to work in. So that gives them a lot of freedom to kind of control their own destiny, not just work on a project that's prefixed. I would like to say that it is true that chemistry is the leading supporter of GRFP. We have more chemistry GRFP than anybody else in the foundation, so we're very happy about that. That also means we get more applications for GRFP than anyone else in the foundation. And GRFP each year reviews 20,000 proposals. So that's a lot of graduate students being supported by the foundation on an annual basis. Broadening participation. NSF reviews all proposals on at least 2 criteria. The first one is intellectual merit, so that's the technical science and what kind of activities you're doing in the research group, and the broader impacts. And broader impacts, everybody always looks at me like, what does that actually mean? What are you doing, broader impacts? Because it doesn't have a very strong definition. And we do want the community to be able to propose what they think is the most important broader impact. So maybe it's your science is going to cure cancer, and that's a broader impact. Or maybe your science is going to train the next generation of students, and that's a broader impact. Another one is broadening participation. And just like ECS, we want to make sure that a very wide variety of people is included in the research. And so we give out what we call age AGAP GRS Fellows. This supports an additional PhD student on your research. So if you have a grant from NSF, you want another student, you can apply for a research supplement. If your university has an AGAP project now or is a legacy AGAP institution, and these are great fellowships. They can be renewed for up to 3 years. And again, it's our way of promoting diversity in the scientific workforce. This is our newest DCL, and I think not many people know about it, so I'm really happy to kind of bring it to this audience because I think it's a natural. Yes?
What is DCL?
Sorry, thank you. DCL is Dear Colleague Letter. So a Dear Colleague Letter, as opposed to a solicitation, means that we don't have a set-aside pool of money for it, but we're announcing that we're very interested in getting the community's attention to propose these kinds of proposals. So thank you very much. So Dear Colleague Letter. And this is on the interns. So what we have noticed is that a lot of graduate students, when they go out for their first job, many in chemistry are going to industry. And sometimes they don't quite have the exact skills that industry really wants. And so what we'd like to do is give them an industrial experience while they're actually in graduate school. And so we're willing to, if you would allow your student to go, and you already, what did I just do? Thank you. I got it. I'm going to put that back. If you would allow your graduate student to partner with an industrial sponsor, we'll pay them to go off to industry. Well, you can keep your money from your award and pay another student. This is a 3 to 6 month internship. Industry doesn't have to come up with anything. They're, free help for them. They can work in a large or small industry, nonprofits, tech transfer offices, and they can go internationally if you can justify it. This is free money. We have gotten applications this year. So please, this is a group that has great industrial ties. Send your students to industry. It's a great opportunity for them. They bring back the knowledge to you. Industry also gets to kind of look over the person, maybe hire them later. It's a great program, but we need more applications. We'd really be happy with more. Another Dear Colleague Letter is the Chemistry International Supplements. So sometimes in the United States, we are very concerned about staying globally competitive. And sometimes there's facilities outside of the U.S. that have a certain instrument or expertise that we just don't seem to have in the United States. We want to send either you or your graduate students or your postdocs to whatever country, go work with them, collaborate, then come back and bring some of that knowledge and good collaborative expertise to the United States. So this is a supplement request. If you have an award, you can write to the program officer. It's a couple pages of justification, not 15, just 3 pages. What you're going to do, with whom, where you're going to be. We pay for your travel. We pay for your room and board. The international partner doesn't need to put any money in. We welcome requests, and almost any country is game for this type of collaboration. So please ask us for these. It's an easy experience, and again, brings back expertise that we might not have in the United States. Other workforce training, we are experiencing kind of a renaissance in workshops and other activities, summer schools, things like that for the community. This one is on the Molecular Sciences Software Institute. So if you're interested in having more expertise in computation and theory, modeling, things like that, this would be the group that chemistry funds. And their job is to give to the community, training in computational chemistry. So they have a program for undergraduates. They're doing Teach the Teachers, so they'll teach you so that you can teach in your classes. So if you're looking for some computational expertise, this might be a way of getting it into your group. Here's another one that I bet if I just say GOALI that half the room would probably not know the acronym for it. So it's Grant Opportunities for Academic Liaisons with Industry. And what that means is that we're looking for investigators from academics to partner with someone from industry. So you both become the PIs for the award. NSF will pay for you to, again, either go yourself or go with your students, and it can be students at any level or postdocs, to the industry to kind of learn what they're doing and bring back and do a collaborative interaction. We cannot pay for the industrial person's salary, but we can pay for expenses that you might incur when you go to the industry and use their NMR or whatever. We really love this as a way of, again, giving expertise, getting more industrially relevant, looking at kind of problems that maybe the fundamental chemistry that NSF funds, can translate into a more applied project. So we're hoping that people take us up on this. You can include a third partner, that's a national lab or a nonprofit group as well. So we're kind of open to partners. The biggest stumbling block, I'll be honest, is we need a signed intellectual property agreement before we can actually make an award. And that's a hard one for people to hammer that out. Who owns what in terms of the materials and the IP. We are super excited whenever we get a goalie proposal, so please, think about this. You just showed us, 50 potential partners on your report this year, so, get working with those sponsors and maybe give your students or yourself a little bit of a extra broader impact when you work with industry. And this is an example of a goalie SUSChem project. So goalie grant opportunities for academic liaisons with industry, SUSChem, sustainable chemistry, engineering, or materials. And just to show you kind of one successful project that we've had. So we're keeping on the industrial theme because, again, I think it's the strength of ECS that you shouldn't hide under a bushel. So this is the I-Core program. Again, very scarcely attended by chemists. If you've ever seen the TV show Shark Tank, where they pitch their ideas, that's what this program does. It's a 6-month training program where NSF, people who work in small business, SBIR, STTR, will actually train you to develop a business model, go into industry and refine your pitch. So you can see if your product is really interesting to the market, assess the value propositions, develop a compelling narrative. The team is 3 people. It's the lead PI, so an academic faculty member usually, the entrepreneurial lead, which is a graduate student or postdoc, and then an I-Core mentor, so that you actually get somebody who's in the industry that you want to propose in to give you advice about contacting 50 companies that might be able to tell you, yes, this will work, no, it won't, what price point you should be asking for, and to really help you get started in business. Again, this is a great program. It's undersubscribed, especially for chemists, and yet we have the chemical industry, which is humongous, the biggest industry in the world, I think. So we really encourage people to be more active in the I-Core program. And this is the way to start. And there we go. Oops, sorry. This is an example, so I hope that you know Carlos Cabrera, University of Puerto Rico. He started with a chemistry division award, and he parlayed that into a small business, got funding from the SBIR, the Small Business Innovation Program, and he was able to kind of get his device, which he looked at the fundamentals of in part of our program, and then actually make his own company. So it's a very successful model if you're interested. CCI, so far I've been talking about kind of individual investigator awards or very small teams. I'd like to expand that to larger teams. So our Centers for Chemical Innovation is one of our programs which we really try to gather large teams. So this is 20, 30, 40, 50 different people in different areas of expertise. It's chemical innovation because many of these centers interact with industry. For example, we have the Center for Sustainable Polymers, interacts with 3M and other industries there. We have some that do catalysis, sustainable nanotechnology. The Center for the Space-Time Limit actually makes its own tools, so they're instrument kind of developers. We have everything from aerosol investigations and kind of looking at how clouds form over the oceans and carry on to the beach. And again, functionalization, a lot of organic chemistry leading to pharmaceutical production. So these are phased proposals. At the first phase, we give 3 to 5 awards to kind of get you started. $1.8 million over 3 years, again, to get preliminary results, kind of gel the team, get working on your innovation platform. And then out of those 3, we down select to 1 that actually becomes a big center, and that's $20 million over 5 years. You can be renewed once. So in total, you're getting almost $42 million to work with a team in some area of chemistry. So highly competitive, but definitely something that is really ripe for some folks. Obviously, DOE has its EFRC program. Engineering has its F-free program, EFRI. This is ours, and we're very proud of this program. This is one of the phase 1s that just got selected. Shelley Mintier, I think some of you probably have heard her talk today or will this afternoon. This is one of her big outstanding results from her phase 1. It's focused on the Birch reduction. So you take elemental sodium, put it in liquid nitrogen at cold temperatures, and they're able to perform a reduction that industrially is very, very difficult electrochemically. And so the pharmaceutical industry is thrilled with this result. And so we're very excited to see this center compete for phase 2 funding in the next year or 2, one of the 3. So how can I, or the division, help you to conduct your work? There are some special facilities, again, that chemists make use of, but it's kind of a quiet secret, so unless you're in the loop, you may not know about it. Chemistry division funds the Fourier transformed cyclotron resonance mass spec at the National High Magnetic Field Lab. So if you're interested in using some mass spec, very powerful at a 21 Tesla magnet, you just submit, again, a small proposal to them. They'll give you instrument time, and while you're there, they'll give you training on the instrument. So if you're interested in getting some really good mass spec results, please contact this group. Chemistry pays for it as a service to everyone, so everybody, whether you have an NSF grant or not, is eligible to apply. This is one of the results that is part of the ICR that we funded. This is the smallest stable fullerene. It's a little bit old now, but it certainly was a great result. They were able to do the mass spec of this molecule and confirm its stability. So it's really, really cool. The other group that we fund is called ChemMatCars. So at Argonne National Lab, at the Advanced Photon Source, chemistry, materials, and now biology and engineering fund a end station on the beamline. And that end station, again, accepts proposals, short proposals. If you get funded, they give you instrument time. So you take your group, you go there. They'll have people who train you, who help you set up the reactor, get the specifications. They work 24/7, so it's a really amazing place for students to do research because they're doing research every minute of the day. This particular end station does high precision crystallography, liquid surface and liquid-liquid interfaces, which might be of interest to the battery community, and small angle X-ray scattering. So if you're interested in any of those techniques, please do use this facility. It's free for you to use. Obviously, you have to travel to get there, but we would love to have more chemists involved, especially from the electrochemistry community. And this is just a highlight of some of the work that was done at ChemMatCars. So I am now talking to you about the NSF's 10 big ideas. So NSF in 2016 really thought hard about what the different needs were for the entire country. And they proposed 10 big ideas, which is Okay, I'll be very honest with you, probably too many. But this is was seen as a budget builder in an election year. Um, and so each of these big ideas has with it at least $30 million of additional funding that people can compete for. So again, we're hoping that the chemistry, materials, engineering communities, make use of these solicitations, and it's all kinds of different areas. So I hope you're familiar with them, and again, avail yourselves, because they each have different solicitations, and you're allowed to propose to these in addition to the chemistry division. So I'll go through those kind of fast. I only have 6 up here. There's some that don't apply to our community all that much. Navigating the New Arctic is one of them. Multi-messenger, signaling, things like that. We're not quite set up to participate in. So these are the ones that I think will give our community the most money. So understanding the rules of life. There are what we hope basic principles that govern all of life. And we've had for many years the Understanding the Brain initiative, which I think a lot of electrochemists have looked into, probes in the brain, looking for electrochemical signals and how the brain actually works. This is kind of the next generation of that, looking at the rules of life in terms of building a synthetic cell. So can we actually build a cell or modify cells that exist to make the products that we are interested in? Can we understand the functions of every part of a cell? Can we look at epigenetics? So it's kind of the influence of the environment on your DNA and how your DNA changes with the environment. So these have been what's been the topics for this year. Next year, the topics have not been announced yet, but if perhaps you ever looked at the National Academy reports on the microbiome, that might be a great topic. Not that I'm saying, but it might be a great topic if you are interested in that to think about proposals in the future. Harnessing the data revolution. Obviously, data is getting huge, especially mass spec data. But if you can think of all the crystallography data, what would happen if we could actually do data mining through Beilstein and other chemistry reference materials? What would chemistry be able to do if we were able to use all of the data, both positive and negative, in predicting reactions for the future? So this is the initiative to kind of start thinking about how chemists can use, we have data that goes back hundreds of years on reactions that work and don't work and reaction conditions and things like that. So how can we engage with computer scientists, mathematicians, and others to really make that data work for us so that we can maybe get the next computer to predict reactions or lead us to new compounds that might be what we would use as synthetic targets. This is also about AI. So it's been proposed a couple times, these high throughput screeners. How are those more effective? How can we get a computer to, tweak reaction conditions in real time to help us synthesize things more effectively, especially on a kind of an intermediate laboratory scale? So again, $30 million for this effort. The chemistry's particular effort is data-driven discovery, science, and chemistry, so I hope that you might take an interest in that. Quantum leap. Again, chemistry has a huge play here. A lot of people think it's materials, and I've seen many people just kind of walk away, oh, that's not chemistry. It certainly is. We are very interested and have had a long tradition of aligning the spin on molecules and looking at them in a convergent way. So this is an example of Dana Friedman's molecule, where she aligns the spin on the metal atoms in the center, and she can hold them in a lattice so that their spins are aligned. And that's the way that they're looking at building the next generation of computers. This is IBM's latest computer. You can see they're very, very intricate. Demands, chemistry works with materials and engineering and other groups to put these computers together. We have been approached several times by Google and Amazon and IBM. They feel that chemistry is the killer app which will prove quantum supremacy. So Everybody's interested in building a quantum computer, something that works on light instead of electrons, because they think this computer will be able to encrypt or de-encrypt data. And that's going to be really important for banking, for medicine, for nuclear facilities, anything where you want those codes to be secure, both on a personal level and at a national level. So we have to be able to know how a quantum computer works. And they're very noisy, and they don't have high fidelity, so you can put the program in and get something else out. That's not very good right now. In order to test whether the quantum computer is better than the regular computer that we're using now, they're going to use quantum chemistry as the test case. And so they're really interested in having people engage on using spectroscopy and solar applications, photosystem 2, nitrogenase, and other biological molecules, and using the quantum chemistry applications on both computers to look which is superior and when does the quantum computer beat, when does the quantum computer beat the regular computers now. So this is a really important initiative in terms of security for the United States. And again, it's very personal. You want your medical records to stay intact. You don't want somebody breaking in that code. So this is something that I think a lot of students are very much engaged in. They're having hackathons and other activities to really promote this idea and what students can do in this area. In terms of workforce training for those students, we have quantum science summer schools. They can go for a week and kind of look at the landscape, maybe try their hand at programming a quantum computer. We also have the triplets program, which is the student, their faculty member, and an industrial collaborator working together in kind of like an incubator type environment to kind of get what industry knows into the hands of a much broader audience. And I'm pressing the wrong button. I am almost finished. So Convergence Research, again, this is beauty for us. We love this initiative. Chemistry is one of the most convergent areas of research there is. So chemists have always worked with biologists and formed a new area called biochemistry that has a language all of its own. It's not really chemistry or biology. It has its own language. It does its own experiments. It really works together very well. We also work very well with people in engineering. That's kind of the catalysis field. We work well with people in materials. So there's no seam between, atoms, molecules, bigger molecules, nanomaterials, bigger, systems of materials. So Convergence Research is trying to pair up, at least in groups of 2 and 3, different areas of science. So maybe chemistry and geoscience, again, atmospheric science, oceanographic chemistry, all kinds of things. So this is a natural. If you have somebody in another field that may not be chemistry, propose to this. It's good money, $30 million. We are looking for people who are on the edges of fields, on the intersections, to work together and really push forward the new areas of science and technology. Mid-scale research infrastructure. So NSF has always had a program called the MRI, Major Research Instrumentation, and that funds instruments up to $4 million, where usually that $4 million is for electron microscopes or really fancy NMRs or things like that. Chemistry has always done very well in those competitions, and we enhanced the MRI program with about $4 million of our own money. So there's a lot of instrumentation that goes out to chemists every year. There's another program called the MREFC, so it's Major Research Equipment and Facilities Construction, that other groups like physics and astronomy use to, hopefully you've heard that they had the Event Horizon telescope looking at black holes. They've had LIGO looking at gravitational waves. They funded a lot of telescopes. These are really big construction projects that NSF owns and usually runs for about 30 to 60 years afterwards. Up until now, there's been a huge gap between that $4 million and the $1 billion LIGO project. And so now we're trying to look at what are the bigger pieces of equipment that we haven't been able to buy or build. And so we're asking the community, what do you need? And maybe for the Electrochemical Society, it might be, a facility to test batteries under, I don't know, human reaction conditions, right? Temperature, time, speeding, either, I don't know. You'll have to tell me what do you need. We'd love you to propose it. So there's two opportunities. One is from 4 million to 20 million, and one is 20 million to 70 million. And those are the two opportunities now. We're running our very first competition, so I don't even know examples of what wins and what, how to put together proposals, but we're certainly very interested in seeing what groups can bring together. It's our biggest opportunity for new development, and to really buy pieces of equipment maybe to put together that would really be needed in the same location to run a very successful research project. So I'm finished with my comments. And again, I would thank everybody at ECS for being so kind in their invitation, but especially to Chris, you, Knock, Shannon, and Melissa Olson is our Presidential Management Fellow. So if you know somebody who's graduating, who might not want a lab position, doesn't want to go into academics, NSF actually does hire people right out of their postdoc as well, and it might be a fun job. So if you have someone like that, please let me know as well. But I thank you very much for your time and attention.
Thank you.
We have time for questions.
Yeah.
So one thing which has changed over time has been the cost of databases. This goes back to data mining. For example, the crystallographic databases, which NIST has maintained, the pricing shot up tremendously on those. That it's almost $4,000 for the licensing. And the thermochemical databases, those sorts of things, those used to be freely available or at very low cost. And it's put a tremendous burden on universities now to maintain up-to-date reference libraries here. And so maybe some thought of how NSF could help support that for the U.S. universities would be really, really helpful.
Could everyone hear the question? So you basically said that the crystallographic databases and the NIST databases that they have of thermodynamic data, the costs of those are really increasing, and I agree completely. So we are considering kind of two avenues to kind of help with those. One would be the data science big idea, but the better fit and where I think a lot of other divisions and directorates are looking for are at the mid-scale. So biology, for example, are looking for seed catalogs. Where they have seeds from all ages, all areas, and that kind of database is very expensive to maintain, yet very important for all of agriculture and things like that. So we haven't received any proposals like that to date. I'm hoping that maybe you could help me get the word out that there is this opportunity that we have in mid-scale. Probably is the easiest one.
There are incredible tools to mine,
Mm-hmm.
actually.
Yeah.
The databases which already exist, it's our ability to access the databases at the current level of information, which is a barrier.
Yeah. So again, yes, it is the access to the database is one, and then maintaining the database is another. And so yes, we have been having a few workshops. So anytime you hear NSF is having a workshop, I hope, just like the Dear Colleague letter, which announces our interest, a workshop also announces our interest and our willingness to get feedback. So we're going to have more workshops where we hope that you give us feedback like that, and that way we can make it actionable probably in the next fiscal year. So yeah, keep saying that. I keep bringing it back. Budgets are always a work in progress, but we're working on it. Yes.
So you brought up big ideas, but I've also seen grand challenges in some of the NSF solicitations. Can you compare and contrast? What is a grand challenge to NSF versus a big idea?
Yeah. So what's a grand challenge versus a big idea? So a big idea is from 2016. It's that term. I think what we would say is, we put forward a smorgasbord of ideas, hoping that some would be acceptable to the president when he made his request for funding for NSF. They didn't make a big selection, so we're doing them all. Grand challenge has probably been I mean, so there's been grand challenges everywhere, but it is a term that DOE often more has the, I don't know, they call their activities grand challenges. So NSF tries to let them hold that title, grand challenges, and we are now doing big ideas. I think they're very similar. They have a ton of overlap, but it's just kind of their term versus our term so that you can have some ownership.
So in that, is it okay to identify a DOE grand challenge in an NSF solicitation?
Sure. Yeah,
That's cool.
absolutely fine. Yeah, if you want to use grand, we read their reports as well, and a lot of times we try to work together. I think electrochemistry is an area that's really ripe for joint interagency collaboration. So we are very much in talking with DOE about what their grand challenges are and how it fits into our big ideas, and going forward in the future, we hope to engage together, especially in the area of electrochemistry. Yes?
So since the NSF division chemistry reorganized itself
Mhm.
7 or 8 years ago or whatever.
Yep.
It doesn't really see, and you mentioned a number of places where we sort of did, but it doesn't seem to be that we have a real home as a discipline anymore. In fact, I've sat on NSF panels in like 4 of those different areas, and it's sometimes they're like, well, we need an electrochemist because we have proposals.
I see.
They're in this field, but then are electrochemistry. And under the old system, I don't know if we had a better home or not, but now that you're sort of application driven or end product driven, it's not really clear to me where electrochemistry fits except in how it's applied to one or
Mm-hmm.
2 particular areas.
So you're absolutely right. So in 2009, the chemistry division reorganized, and we went from inorganic, organic, analytical, and PChem to these topics. And at the time, and I don't even know if you were around to know this, we had an elaborate flow chart where if you were doing synthesis, chemical measurement or imaging, or chemical structure dynamics or mechanisms, those were considered the core things of chemistry. And then at that time, to kind of encourage collaboration outside of the division, because that's where the money was, we invented the catalysis program, which interacts with engineering, the environmental chemical sciences, which interacts with geo, chemistry of life processes with bio, and macro super nano with DMR. And so we spread our tentacles because that's where the money was. Since then, we have really seen that those areas, because they have applications kind of embedded in them, are very, very, very popular. And those are the most popular, oddly, those are the most popular programs that we have. Each one has probably $30 million to spend on their own. So in order not to keep shuffling, you're absolutely right. Electrochemistry is embedded everywhere, but that means everybody is happy to have your proposals. So I think you just have to decide, where is the application, or you're just doing fundamentals. If it's fundamentals, again, it would be synthesis, chemical measurement and imaging, and CSDM A or B, depending on if you're more on the PChem side for A or on the kinetics and thermodynamics of kind of physical, organic, physical, inorganic for CSDM-B. But speaking to the program officers, or I can talk to you about your particular area of research, this is, it really was done to be more applied, to look at the interfaces with other groups. Yeah. Yes, sir?
You mentioned the non-academic research internships,
Mhm.
and you said you need more applications. Who applies?
So the intern would be anybody who's got NSF funding. So if you're from industry, yes, perfect. So what you should do, the easiest way, would go to the nsf.gov website, look up awards search. If anybody has a chemistry division grant, you can approach them, say, hey, I'd like to do an intern. They're usually very, very excited about it, but they would apply to NSF for additional money on top of their research grant.
Okay, so the industry goes to already awarded fund grants.
Yeah, absolutely. And it's not just chemistry that's, working with this program. Most of the directorates and divisions are actually participating in intern program. So almost anybody you can name that you'd like to collaborate with them as a PI, that they're participating in this group. Any other questions? Good. Thank you very much.
Thank you, Carol.